Welcome to homework.
Okay, so we're told that we have a molecule C6H12 and its name is D, just a placeholder name. We're told that it is optically inactive, but that it can be resolved into enantiomers. This tells us that D has a stereocenter. Now, the goal of this question is to determine what D is, in addition to determining what E is. E is the product of D upon catalytic hydrogenation. Catalytic hydrogenation. So the catalytic hydrogenation of D gives E, and E is optically inactive. All right, let's take a crack at this. So likely the best way to go about this would be to determine some possibilities for what D is, and then come back and see if it makes sense for E. So the first thing we can do with D is just look at its molecular formula, C6H12. From that information, we can determine the degree of unsaturation. Degree of unsaturation is essentially telling us how many double bonds and or rings or cyclic structures might we expect in this molecule. A DU is calculated as follows. It's the number of carbons minus the number of hydrogens divided by 2 minus the number of nitrogens and the number of halogens divided by 2 plus 1. So for us, that would mean du equals 6 minus 12 divided by 2 plus 1 minus 0 equals 1. So the degree of unsaturation of D is 1. That means we have at least one double bond or some sort of cyclic structure. Okay, so now we know two things about D essentially. It has a double bond and it has a stereocenter. So where I would go with this is I would start from that stereocenter. Let's say this is the carbon at the center that will be our stereocenter. So we know we must have 1, 2, 3, 4 bonds to this carbon, and that each one must be different. That's essentially what a stereocenter is by definition. So we've got 4 bonds coming from this carbon to different atoms or different chains that aren't identical. So where I would go with this is perhaps it's not totally guess and check. What it is, it's more of an informed guess that we can use to reason about the structure. So for example, if we were to say put a hydrogen here, what would these remaining carbons almost have to be? Well, we know we've got to have a double bond somewhere. So let's arbitrarily decide to put that here. Okay, we put a double bond there. And then we also know that these two carbons here and here can't be the same. So they can't both be methyl groups as they are right now. They also can't be the same as this carbon. So what could we put on one of these carbons to make it different? Let's just try another carbon. Okay, now does our formula make sense at this point? We have 1, 2, 3, 4, 5, 6 carbons. And without necessarily even counting these, I know it's going to have the correct number of hydrogens because any carbon backbone with a single double bond should have n carbons times 2 hydrogens. So since we have 6 carbons, we know we'll have 12 hydrogens. Whereas if we had no double bonds, it would be N times 2 plus 2, or 14. This is really just a reflection of the degree of unsaturation formula. So we know that this structure is a possible valid structure. There may be other structures we could think of, but to be honest, there's almost not other structures that we could pick. Like, so if we started from a central carbon again, and once again, we know we have to have 4 different things. Let's say we make none of them hydrogen. Last time I arbitrarily picked this one to be hydrogen as sort of an informed guess. Instead, let's say this is a carbon, this is a carbon, this is a carbon, and this is a carbon. Well, I still got to put a double bond somewhere. Okay. Now I've got 1, 2, 3, 4, 5, 6 carbons, but these 3 carbons are all identical. So that doesn't work, right? That was kind of my only other option other than putting a hydrogen here, was to put carbons around the central carbon entirely. So I'm fairly certain then that this is the structure of D. Or at least it tracks with the information we have so far. It's got a stereocenter, it's got a double bond. Now, does it make sense that catalytic hydrogenation of D would give us a structure E, which is optically inactive? Well, what would be the product of the catalytic hydrogenation of D? Let's find out. What is catalytic hydrogenation? Catalytic hydrogenation will effectively convert any double bonds in our structure to single bonds. It does this by adding hydrogens across that double bond. It adds a hydrogen here, and adds a hydrogen there to give us a single bond. Okay, so let's consider what that would mean for compound D. Let's draw this a little bit. So it's 1, 2, 3, 1, 2, 3, 4. There's our methyl, hydrogen here, and put our double bond here. Catalytic hydrogenation of D would add hydrogens across this double bond, giving us this molecule. Is this molecule optically inactive, as we were told that E is? Yes, because it has no stereocenters. This has 3 hydrogens, so it can't be a stereocenter. This carbon has 2 hydrogens, can't be a stereocenter. Ditto for this one and this one. This carbon has 1 methyl group and 2 ethyl groups, so since it has 2 ethyl groups, it also can't be a stereocenter. So this should indeed be optically inactive. So D is this structure here, whereas E is this structure.